Okay, before the second break, we complete part 1 and part 2. Part 3. Part 3 just mentioned some problems in the previous derivations. In the previous part 2, we successfully derived our member stability matrix in local coordinate system. And we can find out the force and displacement in local coordinate system. But you can immediately find out some problems. Say, for example, for member 3, we have a truss structures composed of 3 members, 1, 2, 3. They have different orientations. When you apply our previous matrix to member 3, then this becomes the orientations. When you apply our matrix to element 1, vertical, you have different local system. If you apply the things to element 2, you have a diagonal local system. So when you take a look of the common joint, physically, you can combine force, you can add up force together, all the forces together, right? Force is a vector, it supports direct additions, as long as they are along the same directions, right? If force along the same direction, you can add them up together. But when you take a look at this corner, we have horizontal force, we have vertical force, we have diagonal force. They are not in the same direction. They are not in the same directions. So in this case, you cannot directly add up the values. You have to change their directions. That's why it comes to these terms, transformations. You have to transform the orientation so that they are along the same system. And then you can add them up together. Otherwise, just like this picture, you can't join them together because they are pointing along different orientations. This is the things we want to discuss in this part 3, transformations. We are going to transform our matrices to so-called global coordinate system, new terms. Our objective is to transform our force displacement from local to global. We know what is local system. Local system is a system along the length of member. Then what about global? This is the local system. Global system is our conventional coordinate system. Horizontal for X, vertical for Y. Global, same to everyone. We call that global coordinate system. Positive X to the right, positive Y upward. Our task in this chapter, in this part, is to set up the transformation equation, transform the things from local to global. We utilize some transformation angle. Theta X, theta Y. We need this kind of transformations, just like sine cosine in your math. If you want to project, if you want to transform a diagonal line to vertical and horizontal, then what techniques we can use? You can use sine cosine, right? Sine theta, cosine theta, similar things. It's rely on the angle. In the derivation, in the notes, I use 2 angles, theta X, theta Y. They are the angle, the smallest angle measured between the positive global X or global Y axis to the positive X prime axis. Be careful of the target. The angle is measured from global axis to local X prime, not Y prime, okay? No Y prime. It's measured from global axis to local X prime axis only, which means the angle is measured from the global axis to the member, Nothing to do with X, Y prime here. Don't take the wrong directions. Don't take the wrong axis. Then how we do the transformations? Quite simple. I use cosine thetas, cosine theta X, cosine theta Y. I group them into a symbol called lambda. Just make the expression shorter. I don't want to put down cosine many times. I simply use lambda to denote cosine theta X, lambda Y to denote cosine theta y, and so on. How to find out cosine theta x, cosine theta y? In principle, you don't need to directly find out the angle theta. Okay, you don't need to directly find out the angle theta. Why? Say for example, lambda x equal to cosine theta x. What is cosine? You can think about this right angle triangle, right? Cosine theta x means the horizontal length over the length of the member. This is cosine theta x, right? From this picture, if you know the coordinate, this line quite confusing. From this picture, you can find out the coordinate at node n and node f. At node n, the coordinate is xn, yn. At node f, the coordinate is xf, yf. If you know the coordinate at 2 points, I believe that all of you can find out Lx and L. Lx is equal to xf minus xn over L. Length of a diagonal line, you can find out the length easily using 2-point distance formula. So using the coordinate, you can find out lambda x. You don't need to exactly find out the angle. Up to you. Right? If you like, you can find out angle, but I think a more easy way is to use the coordinate to find out lambda x directly instead of doing the angle. When you use this angle sine cosine operation, you have to double check your calculator. Right? Radian, degree, they may have different numbers. Be careful. Lambda x, lambda y, they can be calculated using the coordinate. Suppose you should know the coordinate of a structures, right? I mean, you know the length, you know the height of the structures. You know the height of the structures, you know the width of the structures. Then maybe you can set origin at this point, right? 0, 0. Then you can calculate the remaining coordinate easily of a structures. Using this idea, you can reproduce all the coordinate at all nodes and calculate lambda x, lambda y for all points. Quite easy. Now we have some idea about transformations. You can use cosine theta, to transform the things to the y-axis or to the x-axis. But the thing is that we have two things to transform. One is displacement. The other one is forces. We have to transform them separately. On this slide, you can see a term called displacement transformations. We are going to discuss how to transform displacement first. And then the next part, we discuss how to transform forces. And then you can put them together. Okay, displacement transformations. In session 2, we introduce local displacement. We have dn dx when you explain the displacement of a truss member. But what happens if you want to explain this in global system? From the picture, you can see that for a truss member, we have two possible displacement at each node. One horizontal, one vertical. When you describe displacement in global coordinate, the node may under horizontal or vertical movements. We call that D. I use capital D to denote global displacement. Okay, I use big D to denote global displacement. D and X. D stands for displacement, N stands for the node, X stands for the direction. D and X, D and Y. Similarly, we have dfx, dfy. So you can see that if we want to describe the displacement using global system, then we will have 4 nodal displacement for one truss member. Okay, we have totally 4 global displacement: dnx, dny, dfx, dfy. In the previous part, we have 2 local displacement. Small dx, small dn, and small df. Small d means the local displacement. You can describe displacement in terms of local or global displacement, but they should be consistent to each other. In the following section, we are going to find out the relationship between local to global or global to local. Okay. How to find out their relationship? We apply the same theory, principle of superposition. We apply the displacement separately, and then finally put them all together. We're using superposition once more time to find out their relationship. So let's take a look on these conversions. Same as before, at the beginning, we just consider the possible movements at node n. We fix node f, just focus on node n to make things more easy. For node n may properly under two global displacement, dnx, dny. We consider them separately again. For a member under dnx means the displacement and along horizontal directions. After this displacement, the member deflect horizontally, become the dashed line. Then what is the projections of the global displacement back to the local coordinate? The blue terms, d and x, is the global displacement at node n. If you want to find out the corresponding shortening or elongation along the member, then it becomes the projections along the member, right? How to find out these projections? This is theta x. This is the diagonal length. We found that the length along the member is equal to dnx cosine theta. We can use cosine to project a diagonal line back to the length of member. Similarly, for a member under upward displacement, dny, for a node under upward displacement at node n, we would like to transform this back to the local system along the member. Again, we can use cosine theta y. We use cosine theta y. So for a member under combined dnx and dny, what about the total elongation along the member? The total displacement at node n in local system due to combined dnx and dny is simply equal to superimposing the two results together. It becomes the total displacement in local system, small dn, okay, dn. This equation gives us the relationship between local to global. Capital D means global displacement. They are not totally independent. They have some relationship through this equation. This equation tells us what happened at node n. Then what about node f? Node f, you just repeat the same things again. Apply the global displacement and then project to the local system. At node f, you do the same things. I'm not repeat again. You do the same thing, apply the global displacement, and then find out the projections along the member length. Same operations. Okay, dfx, the effect due to dfx, and the effect due to dfy. Add them up together, it becomes df. The total displacement at f along the member length. Again, we have two similar equations, one for dn, one for df. I replace cosine by lambda to make the equation shorter. We have two similar equations. Why don't we group them together into a matrix? You can group two similar equations together into matrix form. You can always convert them back to separate equation. Say, for example, the first equation, dn equal to the first row times this column vector. Then you can reconstruct the same equations. Here we just put them together in matrix form. so that we can utilize the matrix operation properties. The left-hand side, the right-hand side is a global displacement vector here. The top two elements represent what happened at node N and then node F. This is the global displacement vector, global, big D. The left-hand side one is the local displacement vector, small d, local. In between the global displacement vector and local displacement vector, the middle part, this part, help us to transform from global to local. That's why you may call these displacement transformation matrix. Transform a global displacement back to local. Transform them back to local. This one is for displacement transformations. Symbolically, you can use T. You can use T to denote this transformation matrix. Small d equal to T times big D, symbolically. Well, actually, you don't need to remember this equation. Actually, this one is just something help us to derive the next equation, a more general equation. They are just some help us to derive a more general equation later. But at least this equation tells you how to convert from global to local for displacement. What about force? Force is even more straightforward. Suppose we have a member axial force, Qn, applied at node N. Then what is the component about the global coordinate axis, X and Y? You can easily resolve a diagonal force into horizontal and vertical components. Oh, I draw them directly on the pictures. Right? You can resolve them directly with respect to the global system. I use spec Q. I use spec Q to denote the quantity along the global system. We have Qnx and Qny. You can describe the force in terms of local system or global system. But you can see that global system is more general, right? Because they're all the same for all members. You can add them up together later on. Qnx equal to small n times cosine theta x, Qny equal to Qn times cosine theta y, and so on. Same for the other node F. You just write out the corresponding projections. And then you get a set of similar equations. Same concept. You can group similar equation into a matrix form. So this is our force transformation matrices. The left-hand side is our global force vector, or big Q, global force. The right-hand side, second term, is our local force vector, small q, local force. The matrix in between them is so-called the force transformation matrices. Help us to transform force from local to global. Again, this equation is just a helper, help us to derive a more general formula later. You are not necessary to remember all the things right here. They are just some help. Here, this part is important. It tells you how to derive a more general stiffness matrix for truss element. We know the truss matrix already in part 2, but this is in local system. It's not general enough, right? Right now, we can use the previous transformation equation, convert a problem to a more general manner. Maybe I'll discuss this part next time, okay? This is the first class in the first week.